Hello, welcome back to Piers Rocks. Today we're going to revisit the Diagnostics ROM for these disk drives. I've covered the Diagnostics ROM I built for these disk drives in a previous episode, but I've added quite a few new capabilities, so I wanted to run through both the old and the new in this video. The Diagnostics ROM has three stages. In the first stage, it goes through and it tests all of the main components on the digital logic PCB. The second stage is it uses the LEDs on the front of the disk drive to report any failed components. And then the third stage is it enables the IEEE-488 bus on the disk drive and allows you to connect in either with a PET or a PC, retrieve the diagnostics information over the bus, and also control the physical drive units, enabling and disabling the spindle motors and also executing the head stepper motors. We're going to start off by looking at stages 1 and 2. I have the disk drive dismantled in front of me. That's to make it easier to film and also to make it easier to remove some of these chips for testing purposes. So I have the PCB flat on the bench in front of me, and I have the main drive unit here propped up on its end, so you can see the two drive LEDs and the error LED in the middle. They're connected together using the usual cables. Let's just talk about some safety precautions. When you're operating the PCB for these disk drives outside of the case, these two ground points, which are normally connected together via the case, are no longer connected. So you can see here I've connected them together with a green crop clip. Do that. Secondly, if you're working on these drives, I highly recommend using an anti-static wrist strap so you don't risk frying any of these chips with static. And finally, there's mains electricity in near the transformer of this unit, so don't put your fingers anywhere you shouldn't. The first thing you need to do is head over to the GitHub page for this project, which will be down in the description, and grab one of the ROM images for your drive. There's ROM images for the different types of drives. There's one image for the 2040, 3040 and 4040, and a different image for the 8050 and 8250. I haven't yet been able to test the 8050 and 8250s, but that has an 8 kilobyte ROM image for those drives and loads at a different address. This unit takes a 4 kilobyte ROM image and loads at the F1000 address, which is this socket here. I have a rather Heath Robinson looking contraption here, which is a replacement 2332 ROM. The ROM's in at least my drive. The 2332's, the chip select 1 line is active low and the chip select 2 line is active high. So this little breadboard just flips one of the two chip select lines, so this will work. So you need to install your ROM the right way round in this ROM socket. If you have DOS1 ROMs in your drive, you can actually, there's a version of the ROM that you can install here and leave your standard ROMs in the drive. You can actually always leave the low ROM in here if you're happy that that's a working chip. It's just easier to have the ROM chips removed for an initial test, because then you're confirming that the ROM chips themselves aren't bad and aren't causing problems on the rest of the bus. So you install your ROM chip in the drive, making sure you get the orientation correct. Then you power on your disk drive. Now, last time I powered this drive on, it was working fine. So we shouldn't get any failures from this unit. What we're expecting to see is a bunch of activity from these LEDs on the front of the drive as it runs through its tests. And then it should sit there on a cycle with the error LED off, flashing both drive LEDs the number of times to indicate the hardware device ID for this circuit board. And this is configured for device 8, so we should see both LEDs flashing 8 times, pausing, and flashing 8 times again. Again, the error LED should remain off. That shows that the Diagnostics ROM didn't hit any errors. So I'll power it on. So it's going through and running its RAM tests at the moment. There we go. It's completed all of its tests successfully, and now it's sitting there with the error LED off, flashing both drive LEDs 8 times to signify the drive number for this unit. In terms of the components that have been tested, obviously the Diagnostics ROM itself must be working. This 6502 is running the Diagnostics ROM, so that's working. It's tested both of these two RIOT chips, 6532 chips. These provide together the 256 bytes of 0 page used by this processor. It's tested all of these static RAM chips. There's a total of 4K of static RAM in this disk drive. Those have been tested. By inference, it's tested these RAM bus address multiplex chips, 74 LS157s. It's tested this 6504 secondary processor. It's tested this 6530 RIOT chip and this 6522 VIA chip. Let's start introducing some failures. There are two chips alongside the Diagnostics ROM itself that are required for the Diagnostics ROM to operate successfully. The 6502, because that's the processor that's running the code. And this RIOT chip, this 6532 RIOT chip. In fact, this isn't required for the diagnostics to run, but it drives the LEDs on the front of the disk drive. So if this RIOT chip isn't working, you won't see any output from the Diagnostics ROM. So let's simulate a failure of this 6532 and see what we see. So this is the behavior you'll see if the Diagnostics ROM is dead, or the 6502 is dead, or this 6532 is dead or missing. This signifies a failure to boot. In fact, because we've removed this 6532, the system has booted, the Diagnostics ROM is running, and it's trying to flash this drive LED to indicate that this chip has failed. But that flashing isn't going to work because there's no chip there to actually flash the LED. You'll see the same error code if this 6502 is dead. Now, you'll also see this if any of the other components that sits on the shared data bus has failed in a way where it is corrupting or influencing the data bus and preventing the 6502 from accessing the Diagnostics ROM or the 6502 from controlling this chip to control the LEDs. Now, there are two processors here, this processor, and they share a data bus. They don't share the address bus, but they do share the data bus. So all of these chips are across the data bus. So any one of these chips failing can actually cause this problem. If you get this and you replace your 6502, you replace this RIOT chip, and you double check your Diagnostics ROM, if you're still getting this error, then you're in a game of pulling chips until the drive actually boots and the Diagnostics ROM boots. Now I've replaced the original 6532 and I've pulled the other one. And so this is simulating a failure of this component. This provides half of the 0 page for the 6502. The Diagnostics ROM doesn't care. It only needs 128 bytes of 0 page to operate, so it runs absolutely fine without this chip installed. So we should see when we power it on, it goes through all of its testing again, and then it should report a failure of this component. And the way it will do that is by lighting the error LED and flashing this 5 times to signify that it's the right chip that has failed, and it's this one. If this chip has failed, it tries to flash this LED, but if this chip has failed in a way where the LEDs can't be controlled, then you won't see that flashing. You'll see all of the lights staying on as we saw previously. So let's turn it on. So it's booted, it's going through its testing, it's testing all of this RAM, then goes and tries to test the 6504. Now we see 5 flashes from this drive LED with the error LED lit. Then it goes and flashes its device ID without the error LED lit. Then it will go back into the sequence of showing any errors, so it's showing this chip has failed. Now let's simulate a failure of one of the ROM chips. Now, not all ROM is equal as far as the Diagnostics ROM is concerned. So we have the first kilobyte, the second kilobyte, the third kilobyte, and the fourth kilobyte. And each of these chips provides 4 bits of RAM. So the Diagnostics ROM uses this first K to communicate with the secondary processor, and it has to use that first K. So if either of these two ROM chips has failed, it will bail out of its testing fairly early on and not attempt to test the 6504. When we get a failure of one or more RAM chips, we get an error reported again with a flash code with the error LED being turned on. And we get one flash for one of these chips, two flashes for one of these chips, three flashes for one of these chips, and four flashes for one of these chips. And we get the right-hand LED, I think, flashes for this bank, and the left LED flashes for this bank. So if this chip has failed, we'll get one flash here. If this chip has failed, we'll get four flashes here. So I'm going to remove one of the first kilobyte of RAM chips first of all, and show you the Diagnostics ROM exiting fairly early on and reporting an error with this RAM chip. So it's running through its tests. And we saw one flash from this LED with the error LED lit. There we go. So it's detected this RAM chip has failed, and it's not done any testing of the 6504 side of the circuit. So let's just remove one of the higher RAM chips and test that. It's running through its RAM tests. It goes really fast at the end of the RAM test because it detects a failure very early on. It tests the 6504, and then it flashed this LED with the error LED lit 4 times to signify this RAM chip had failed. We'll now simulate a failure of the 6504 by pulling it out of the circuit. Now we're also going to pull this RIOT chip out at the same time, because if this is not being clocked by the 6504, then it has a tendency to corrupt the shared data bus and prevent the Diagnostics ROM from booting. So that's something to bear in mind if you're seeing the system failing to boot. It could be one of these chips on the data bus. So now we'll turn it on. The RAM testing should all complete successfully, but we should see one flash of both drive LEDs at the end with the error LED lit. One flash of both of them means that this CPU didn't even boot. So it's running through its RAM testing, and it tries to test the 6504. Now it will report the error. So there we go. We got one flash of both of these with the error LED lit to signify that the 6504 had failed. There's actually a second failure mode of the 6504 that the Diagnostics ROM can detect and report. So right now what it's doing is detecting that it boots. When the 6504 boots, it writes some specific values to a few bytes of shared RAM, so the main processor and Diagnostics ROM can detect that. If it boots and does that, then the next thing that Diagnostics ROM does is it tries to take control of the 6504 by sending it some code to execute via the shared RAM. If that fails, maybe there is still a problem with some of this shared RAM, then it will report 2 flashes with both drive LEDs with the error LED lit. Now, in terms of full functionality of the Diagnostics ROM, you can be missing this RIOT chip and these 6 RAM chips, the upper 6 RAM chips, for the Diagnostics ROM to operate perfectly successfully. You can also be missing the 6504 chip and its supporting circuitry for the Diagnostics ROM to run through its entire suite of tests. Once you've reached a stage where the Diagnostics ROM is not reporting any errors, it's just flashing its device ID using the drive LEDs with the error LED off. The next thing you can do with the Diagnostics ROM is you can actually communicate with the Diagnostics ROM using IEEE-488. And this will test the IEEE-488 bus and whether it's working. The things you can do with the Diagnostics ROM are you can query via your PET or via a PC with an IEEE-488 dongle the detailed results that the Diagnostics ROM found when it ran the tests. You can also use the Diagnostics ROM to control the drive mechanisms themselves, control the spindle motors and the stepper motors. And the way it does that is it sends a routine over to the 6504, which controls the physical disk drive units via the shared RAM, and enables the IEEE-488 bus and allows you, the user, to actually control the drive unit. So you can check for any physical deficiencies with your drive units, either the spindle motors failing to start or stop on command, or the stepper motors not behaving normally. I've put the chips back in the circuit board. I've rearranged things so you can see the drive unit now on the desk in front of me, and I've hooked up my Linux PC to the IEEE-488 port of this disk drive. It's booted, it's passed the tests, it's flashing its device ID, so we can use OpenCBM to query the status of the disk drive, and we get the boot status back from the disk drive, and we can see that it's running the Diagnostics ROM. If we query that status again, we'll get a status of 00, just like a standard Commodore disk drive. And Diagnostics ROM is supporting essentially the same IEEE-488 protocol as a standard disk drive, so you can run some of the same commands. You can instruct it to go into talk mode, in which case it will report its status like this. You can also put it into listen mode and it will accept a single character commands. For example, I can send it a command to cause it to reboot, and I use Z to cause the drive to reboot. I can see if it's rebooted and it's running through its diagnostics test. Once it's finished that and ready to talk to me again, I'll rerun the status command and we should see the boot string again. There we go, it's completed, so we get the boot string again. What else can we do? We can instruct the drive to enter command mode, and this stops it flashing the LEDs, reporting any errors and the drive status, and tells it to wait for commands. So when I do that, I get a single LED on one of the two drive units, and it's drive unit 0, and that's showing me that it's in command mode and drive unit 0 is selected. I can then use the M command to turn the spindle motor on that particular drive unit. Now, that hasn't done anything, and I think I've been seeing failures of this spindle motor. So let me just turn that off. I will select drive unit 1. Now the drive unit 1's LED is turned on, and I can run the M command, and I'm sure you can hear that the spindle motor for this drive unit is running. So I'll turn that off. I'll go back to drive 0 and try again, and we're getting nothing. So there's a problem almost certainly with this physical drive unit, and I have been seeing this on and off. The other thing we can do is we can control the spindle motors. So I still have drive 0 selected, and I can bump the spindle motor. So this will drive it back and bump the heads at the track 0 or track 1 stop. So I expect you can hear that it was bumping there. In fact, I think the spindle motor was already at track 0, so it didn't have to travel anywhere. I can cause it to go to track 35 by sending the E or end command. So you saw the spindle motor head move all the way forward, and then I can take it back with another bump command. Obviously I can run the same commands on the first drive unit, but you won't see very much because the drive controller PCB is in the way. Now you don't have to use the OpenCBM commands to drive the disk drive. There's a dedicated support program for PC as part of the Diagnostics ROM repo. So if I run this PC support command with E, it should drive this head all the way forward. There we go. And you see this also provides us a status response. That's not fully implemented, so you can't always trust the OK response from the Diagnostics ROM. And then I pull it all the way back. Now, as well as moving it all the way to either end, there's a command to let you move it an individual stepper motor step. So the stepper motor step is a half track. So when you're issuing the end command, it's actually driving it forward 68 half tracks to take it from track 0 to the end. And just a word of caution, it may be possible to damage your disk drive if you use the end command to drive the head forward 68 half tracks and you didn't start from track 0. So be careful about that. I don't know if it damages the disk drive. I've done it a few times and performed essentially what's a reverse bump, so bumping at this end of the drive mechanism, and my drive unit still seems to be working, but your mileage might vary. Only ever run the end command if you've bumped the head first. The stock ROM for the secondary processor will only allow commands to be executed on drives after a bump has taken place, presumably for safety's sake. Now you can move the stepper motor a half track at a time. You can move it a half track forward with F. And you may or may not be able to see that moving on the video. I can assure you it is moving, and I can hear it moving as well. You can also send in a number of iterations, so if you want to move it forward 20 half tracks. And then you can also reverse that, so you can take it back 1 or 5, or you can perform your own bump. Just like that. So by sending it forward a certain number of tracks, and then sending it back the same number of tracks, you can confirm that the head finished where it started, and therefore you have a good stepper motor mechanism in your drive. Something else I wanted to show you. You can take the drive back out of command mode with X, and this causes the drive to re-enter its flash code mode, so it will use flash codes to report any errors, and it will also flash the device ID. It's doing that now. Obviously, we looked at querying the status previously. This is instructing the Diagnostics ROM to talk on channel 15, the standard status channel for these disk drives, and it provides its status results. The Diagnostics ROM also supports talking on other channels. So if we instruct it to talk on channel 0 and then read data from the bus, this is reading data from the disk drive, then it provides us a list of the channels that it actually supports and the information that it provides. We looked at channel 15 already. This is channel 0. So let's look at the other ones. Let's drive it to talk on channel 1 and look at the summary. There we go, all tests passed. Now let's look at channel 2. And we see a more detailed status from the drive of all the tests that it ran and their status. If we had a failed RAM chip, then we would see exactly which RAM chip appearing here. So I've pulled UE5, static RAM chip UE5, out of the drive, and it has run a diagnostics test, and it's booted, and it's running fine, although it's reporting using flash codes that that chip is missing. So let's now rerun the talk command and read data from the drive, and it tells us UE5 has failed. If we were missing any of the other RAM chips or all of the other RAM chips, it would report all of those to us here as well. I've turned the drive off. I've removed the 6504 processor and also its RIOT chip, 6530, because when that's not driven by the 6504, it tends to corrupt the shared data bus. I've turned the drive back on. It's booted. It's reporting some errors. Let's just look at the summary. Tests failed. Well, what tests failed? Well, I haven't put UE5 back in, so that's failed, but also you can see that the 6504 boot test failed and the takeover test wasn't attempted. And finally, just to whet your appetite, I've been working on a PET support program for the Diagnostics ROM as well. So you don't need to use a PC to drive the spindle motor and the head stepper motors. You can use the PET and you can query all the information that we just saw using the PET. That's not fully operational, but I expect it will be soon. I hope you found this video interesting and useful. If you've got any suggestions for other capabilities I can add to the Diagnostics ROM, please do stick them down in the comments. Also, feel free to make changes, modifications, and submit pull requests on GitHub. I hope you enjoyed this video. If you did, please do stick around. Until next time, rock on.